order for homology and the spectral sequence of branch double cover.
Great. Well, thank you very much for coming. So I'm trying to give a talk now, which I've attempted to give many times before. And I never really got around to the point. I spend usually most of my time defining the bordered algebra. So today I'm going to structure things differently. First of all, I have 5 minutes less. Second of all, I decided to start earlier. So we'll see how that goes. And I thought I would start by, okay, fine. Anyway, so we'll see how far I get in this. So what I'd like to talk about is a relationship between two invariants. And those are Heegaard-Floer homology and on the one hand, and on the other hand is Khovanov homology. And there's a certain relationship between these two invariants. There no doubt are many other relationships, but the one I'm going to talk about today is a certain spectral sequence. And I guess the punchline of today's talk, if I actually manage to get there, is that we actually know how to compute that spectral sequence completely. But before I do that, I want to give some background on the players, some background on Heegaard-Floer homology especially. I'm going to say something about Khovanov homology as well. In fact, what I'll say about Heegaard-Floer homology will be enough to define Khovanov homology. And then I would like to state a relationship between these two invariants. So for a while, I'll be talking about joint work with Zoltan Subel. So Heegaard-Floer homology is an invariant for three manifolds, which is defined by some constructions from symplectic geometry. I want to say almost nothing about the definition, but I'm going to mainly talk about properties. But in case you just beamed in from Mars, I'll give you a 2-minute description, which will be enough to reconstruct the definition. So you start from a Heegaard diagram for a three-manifold, which is specified by a genus G surface and a G tuple of alpha circles and another G tuple of circles called beta. And, you know, I'm going to draw for you a diagram for S3 for some reason. And a base point, which we'll call Z, which is disjoint from them. The construction takes a symplectic manifold, which is the G-fold symmetric product of sigma, equipped with a pair of half-dimensional tori, which are the product of the alpha circles. So these are, in this case, this is G equals 3. We're going to look at triples of points where one point lives on each alpha circle. That defines a three-dimensional torus. I'm going to call that T alpha. There's another torus called T beta, corresponding to the beta circles. And these are a pair of Lagrangians, and what we're going to, the Heegaard-Floer homology of our three-manifold will be, by definition, the Lagrangian Floer homology of the G-fold symmetric product of sigma with respect to these two tori. So that's the definition. The generators are intersection points between these tori. So in this picture, this triple of points represents a single intersection point between those two tori. In fact, that's the only intersection point between the two tori. The generators are the intersection points between the tori, and the differentials count certain holomorphic disks. If here's T alpha and here's T beta, if I've got a generator X and I've got a generator Y, then the Y coefficient of dx counts all the rigid pseudo-holomorphic disks that interpolate between X and Y with their left arc in alpha and right arc in beta. OK, so maybe a few words of apology. The way we originally set this up, we didn't actually quote Lagrangian Floer homology. We didn't construct a symplectic form for which these were Lagrangian. They were just totally real. We had the same energy bounds, so we were able to prove that it's still the same constructions from Lagrangian Floer homology work. And it was really Tim Peretz who constructed a symplectic form that allowed you to say what I just said without lying a little bit. Okay, so that was Heegaard-Floer homology. And let me say some of its simplest properties. So,
sorry, I probably didn't mean from Mars, but what's the big Y?
that's a three-manifold. So this picture, this surface specified by the alpha circles and the beta circles, this specifies a three-manifold. And it specifies it by, you fill in with a handle body where these circles bound inside, and another one that bound on the other side, and that's what gives you a three-manifold Y. And kind of what you might say is that it's bizarre that this should be a three-manifold invariant. It looks like it depends on this picture. And in fact, a lot of the dependence on the picture, the fact that it doesn't depend on, well, the differential involves a pseudo-holomorphic, it's counting pseudo-holomorphic disks. So you could say, well, there's sort of a standard package that says that it's independent of that choice. But the Heegaard diagram itself is some kind of combinatorial choice you make when you draw a three-manifold. A three-manifold has lots of different Heegaard decompositions. And we proved that it was independent of those. And the guiding principle was that we were trying to mimic, we were trying to understand Seiberg-Witten Floer homology. So that was our guiding principle. That was what gave us a guess for what the three-manifold invariant ought to be. Then we proved that it's a three-manifold invariant, but we were both too lazy and incompetent to prove that it's isomorphic to Seiberg-Witten theory. But apparently that has been actually done much more recently. I mean, this is isomorphic to a certain construction in Seiberg-Witten theory, which, all right, I should say a few more things. Oh, first of all, this is not the symmetric product of G, it's the punctured symmetric product of Z, of sigma. And second of all, there are different ways you can handle that base point Z. You could count holomorphic disks that cross Z in an interesting way, and then you get other variants of this construction. So this is the simplest invariant version of Heegaard-Floer homology, HF hat. All right, so now let me say some of its basic properties. The first is that actually I've just drawn a Heegaard diagram for S3. It had a single generator, can't have any differentials. So the Heegaard-Floer homology of S3 is, oh, and by the way, today I will always be using Z2 coefficients. Some of what I say works over Z coefficients, and some of it is actually slightly wrong over Z coefficients. Some of the things that I'll say over Z coefficients are right up to sign. So, so let's just work Z2. So the Floer homology of S3 is one-dimensional. Let me draw, so actually I didn't draw the best Heegaard diagram for S3. Maybe a better Heegaard diagram is this. This is a handle, and this red circle runs through the handle, and there's a single intersection point, P. Actually, Eliashberg says that we should use the sphere, which is the zeroth symmetric product of the sphere, with the two Lagrangians in them, which are the zeroth symmetric product of the empty set. And so you're doing Lagrangian homology of 2 points inside of a point. But that I prefer to stabilize ones. OK, so that's the HF hat of S2 times S1. For S2 times S1, we're going to draw the same torus. This is identified with that. But we're going to have now two circles, alpha and beta, which are parallel sort of to each other, except they're not. They're going to be slight displacement copies of one another. Having a generator P and another generator Q. And you see sitting right in your face a holomorphic disk by the Riemann mapping theorem that connects from P to Q, and another one that connects from P to Q as well. So they cancel in a differential, and what you see is the homology of a circle. So for S1 times S2, we have two generators, Z2 and Z2. And probably that'll be enough for the purpose of this talk. I want to say one other thing, which is that Heegaard-Floer homology is functorial under cobordisms. And I want to describe the simplest cobordism. There's a natural two-handle cobordism from S3 to S2 times S1, and a natural two-handle cobordism from S2 times S1 to S3. And in a certain sense, in a certain natural sense, this Z2 should be thought of as graded in degree 0. This should be thought of as in degree 1/2, and this should be thought of as degree minus 1/2. And both of those two-handle cobordisms drop degree by 1/2. So the generator of Z2 is mapped by the first cobordism to the lower of these Z2s, and by the second one It's the top that gets mapped to here, and the bottom one gets mapped to 0. So these are the maps induced by the simplest two-handle you can draw, a single two-handle that goes from S3 to S2 times S1, and from S2 times, and from the other handle when you turn it backwards. Okay? All right, so that's all. That's what I want to say about Heegaard Floer homology. All right, so this was this invariant. It appeared around 2000, and there was around 2000 there appeared another not invariant, which was by Khovanov. Actually, I think we knew about it already. He told me about it in '97. I don't know. His invariant is, oh, I'm sorry. I need to say one other property of Heegaard Floer homology, which I think is the most important property of Heegaard Floer homology. The most important property, in my opinion, of Heegaard Floer homology is the following. There are exact triangles in Heegaard Floer homology, which are gotten as follows. Suppose I have a three-manifold with a torus boundary, which, of course, I'm going to think of as a knot complement. Just my prejudice. But if I have a three-manifold with torus boundary, I choose a framing of the boundary. Then there are a bunch of naturally associated three-manifolds you could write down, but I want to consider three of them. So I'm going to get them by attaching a solid torus. And how do I attach a solid torus? Well, I've got a torus boundary of my M, and that comes net with I'm going to fix a meridian for that torus and a longitude, which are two curves that intersect in a single point. And I could either fill in by adding a solid torus along the meridian, or I could fill in the solid torus attached along the longitude, or I can look at the meridian plus the longitude. And let's call this a triple of three manifolds. It might look asymmetric the way I drew it, but if you draw the torus as a hexagon with opposite sides identifications, you see that the three curves are perfectly symmetric. And the statement, at least, they're cyclically symmetric. The theorem states that there's a long exact sequence that relates the Heegaard Floer homology of Y filled in with lambda, the Heegaard Floer homology of mu, lambda, and mu plus lambda. Now, we proved this around 2000, but in fact, we were inspired by much earlier work. There was work of Floer in instanton Floer. He showed there was an analogous triangle connecting certain versions of instanton Floer homology, and there's a paper of Brahm and Donaldson, which one can actually read and understand. So anyway, the fact that Heegaard Floer homology satisfied this was really inspired by gauge theory, and we thought of it as further evidence supporting the conjecture that Heegaard Floer homology is Seiberg-Witten Floer homology. Okay, so I said this thing, and now I want to say some things about Khovanov homology. So. I can't see the blackboard when I'm sitting in the audience, which is fine if you're speaking. But if you can't see the time, then you have to take out your cell phone. I'm not calling home. Great. So I want to say a few words about Khovanov homology. So Khovanov defined an invariant of links, which is a bigraded theory. We're going to drop one of the gradings, so I'm actually not even going to talk about it. But I want to say how the chain complex is defined. So the chain complex is defined in such a way that it satisfies a a certain skein relation. So this is an invariant for links. And remember, I'm today working with Z2 coefficients. So so the invariant is by construction. It satisfies an exact triangle which connects the Khovanov homology of a link with a certain crossing in it, the Khovanov homology of a link with that crossing resolved this way, and the Khovanov homology of that crossing resolved this way. And, oh, okay, fine. All right, if you want to be honest. Okay, so this is how it's defined. And say again, what? Which arrow, what? Yeah? Which arrow increases? Well, this is a, why didn't you ask that there? Let me answer the question here. So I said these are symmetric. In fact, there's a funny kind of asymmetry. These maps are induced by cobordisms between three manifolds. And it's not hard. It's a not hard exercise in linear algebra that among these three cobordisms, well, there are two cases. Either all three manifolds have the same first Betti number, and if they do, then exactly one of those cobordisms is positive definite. The other two are negative definite. And the positive definite cobordism is the one that's going to drop gratings. Okay, and now I'm supposed to answer this question over here. It works the same way for the gratings that I care about. So you have to look at the, I mean, this is, of course, I mean, in reality, yeah, so I'm going to look at sort of a Z2 graded collapsed version of Khovanov homology. And the gratings, the way to say it maybe nicely is to say that you look at the determinants of the links. And one of the determinants is the sum of the other two. And it's the one that connects the two smaller determinant knots that has the grading shift for the grading that I care about.
Characteristic of the cobordism.
Pardon?
Cannot be expressed as a characteristic of the cobordism.
It's not the Euler characteristic. It's the signature.
But what's the signature? I mean, we're talking about two cobordisms, right?
Oh, well, of course, I always take branch double covers. Okay, I'm sorry. Let me, okay. So I said the punchline. I'm not supposed to say it yet. I'm supposed to hold it back. Okay, so his invariant is defined to satisfy this kind of triangle. And it's wired to do it. So what he does is he considers a link diagram. You number the crossings. And each crossing, you can either stick a 0 on it or a 1. And if I order the crossings, then I now have a cube, which is so here I put 0, 0. This is 0, 0, 0, 0. Maybe I do 1, 0. That's going to look like this. Or I could do 0, 1. Or I can do 1, 1. But the point is that if you have an n crossing knot, you can write down a hypercube in, 2 to the n different vertices, where you put the zeros or the ones at the various vertices. And then you apply a certain TQFT to these vertices. And the way I like to say it, we're working with Z2 coefficients, I think of it as the exterior algebra on the circles. And the key point is that if I have, well, okay, I have to, if I go from from one circle to two circles, this is a white line. If I go from one circle to two circles, that sends a Z2 a Z2 plus Z2, and it takes the generator to the lower generator. So how to say this right? We're going to, at each vertex, we're going to put the homology of a torus, and the dimension is going to be the number of components. And along each edge, what happens? Either two components merge, or one component splits in two. So the homology of this torus is splits into different tensor factors, one for each circle. And what we're going to say is that the generators from the if a circle splits in two, then the two generators are going to be mapped to two lower generators. And if two circles come together, then the two top generators get mapped to the two generators. Yes.
Do we treat that as a Z2 graded?
Do we treat this as a Z2 graded vector space? Of course, I'm now dropping a lot of the structure from Khovanov homology. I think at this point, let me try to make a true statement. Yeah, let's think of the vertices as Z2 graded, and then of course I should tell you what Z2 grading it is on this. And I think it's the lower one. So it's like the zeroth exterior product of the circles is in dimension 0. Okay, great. Now, here's the relationship between these two constructions. If I have an unlink with n components, then Khovanov would naturally associate to that the homology of the n-dimensional torus. However, if you take the branch double cover, then what's the branch double cover of a disjoint union of n circles? Well, here's a fun exercise in topology. This is just the S1 times S2 n time. It's n minus first connect sum with itself. And the Heegaard-Floer homology, HF hat of that, is the homology of the n minus one dimensional torus. So we're off by one torus factor. But there are two natural ways of remedying that. One is that we could look at what's called reduced Khovanov homology, which is kind of half of Khovanov homology. And then the other thing you could do is you could not take the branch double cover of your unlink, but throw in an extra unknot. That's the other way to correct this problem. All right, so this is a superficial similarity between the two stories. A deeper similarity between the two stories is the following little observation. Suppose I have a link, and I try to take, so if I've got a link inside of S3, I can take its branch double cover, which is a new 3-manifold with a 2-to-1 map to S3, which is generically 2-to-1 map, which is 1-to-1 right along the locus of the link itself. And that's a nice 3-manifold. I can try to take its Heegaard-Floer homology, like I did over here. And let's see what happens to these 3 different links as I take their branch double covers. Well, I've got some complicated link on the outside, but that stays the same for all 3 manifolds. Well, I'm changing only the local picture. Locally, what I have is the branch double cover of the ball branched along 2 arcs that go through it. That's this picture. And this is the branch double cover of the ball branched along these 2 arcs instead. Now, it's an elementary exercise to see the branch double cover of the ball branched along 2 arcs is a torus, always. And if you go through and you check the conventions, these 3 manifolds are related in exactly the way that those 3 manifolds are related, except actually there's a mirror, so the conventions are a little bit different. But so what we're supposed to notice is that the Heegaard-Floer homology of the branch double cover of this 3-manifold and the Heegaard-Floer homology of the branch double cover of this 3-manifold of this knot. Sorry. The Heegaard-Floer is a branch double cover of this link. The Heegaard-Floer is a branch double of this link, and the Heegaard-Floer homology of the branch double cover of this link are related by that long exact sequence, which is reminiscent of Khovanov. So you might conjecture that the reduced Khovanov homology of a link is related to the Heegaard-Floer homology of the branch double cover of the link. And actually, to make it correct, you have to put the mirror of L. And in fact, when I sort of first started thinking about this, I thought, well, surely the two theories must be the same. They're the same on the unlink, and they satisfy the same exact sequence. You should be able to build up anything by looking at an exact sequence. That's, of course, wrong. But the theorem is, this is my Newton's old time, from around 2003, is that there exists a spectral sequence whose E2 term is the reduced Khovanov homology of the mirror, and which converges to an E infinity term, which is the Heegaard-Floer homology branch double cover of a knot. Now, that's really cool because it means you can say the word spectral sequence even if you're a low-dimensional topologist. And I really like that. There are some cases where this really gives information. So for example, if the Heegaard-Floer, so I should say the Euler characteristic of the Heegaard-Floer homology of the branch double cover of a link is equal to the determinant of the link, with the understanding that the determinant is 0 in this. No, there's no understanding at all. This is true. It's the number of elements in the first homology of the branch double cover. It's the Alexander polynomial of -1. Okay, so that gives you a lower bound on the rank of the Heegaard-Floer homology, and for certain knots, the Khovanov homology has that as its total rank. So for such knots, you know the spectral sequence collapses. So it follows, for example, that if L is an alternating knot, then it was known that by work of Lee, that the total rank of the reduced Khovanov homology of the mirror of L is equal to the determinant of the link, and that's also equal to now, by this theorem, the rank of the Heegaard-Floer homology of the branch double cover. You can see this much more directly as well. But anyway, that's the kind of thing that one can deduce from this spectral sequence. However, and you can milk it for a while, because there are other links for which the reduced Khovanov homology is equal to the determinant, and that has something that means the Heegaard-Floer homology of the branch double cover. But there are examples where there's a sincere inequality. So the simplest example is the 3-5 torus knot. You can see kind of immediately it's Jones polynomial. It has, I think, 3 non-zero coefficients in it, if I remember correctly. But the Heegaard-Floer homology of the branch double cover, which is the Poincare homology sphere, has only one-dimensional. It's only one-dimensional. So this spectral sequence must have non-trivial differentials in it. Okay, so this was the state of affairs around 2003. So now I want to talk about, so that is to say, I've now explained what the second part of my title means. That's the spectral sequence of a branch double cover. Now I want to talk a little bit about bordered Floer homology. But maybe before I do that, I'll pause. Are there any questions? Maybe I should say a word or two about the spectral sequence. I've stated it for branch double covers. In fact, it's a more general construction. You can think of it as a way of iterating the exact triangle. So the triangle is about what happens if you have a knot with a framed, three-manifold with a framed knot in it. Then there's a relationship between the Heegaard-Floer homology of the three-manifold the 0 framing on the knot and the 1 framing on the knot. Well, what happens if instead of a knot you have a link, a many-component link? Well, then there's a similar looking spectral sequence, and this is a special case of that spectral sequence. Maybe I could just say that a little in a little bit more words. The branch double cover of this arc is a knot inside of the branch double cover of this 3 manifold. When I do surgery on that arc, I obtain this 3 manifold. So that's a sort of dictionary for going between these surgery pictures and these branch double cover pictures. And I should say that there have been a number of kind of advances over this spectral sequence. Grigsby and Verley proved a version for some colored Khovanov homologies converging to a certain other Heegaard-Floer construction. Beautiful. So that you transition between concerns have. To work on that HF has really cool. If I then I have to do violence to it. I have to push the curves all over the place to make many, many, many different regions. And at the end of the day, if you end up with a Heegaard diagram which has the following properties, the complement of the alpha and the beta circles are just a bunch of squares and rectangles and bigons. Well, then there's some Euler characteristic problem. But you might have one additional polygon. You understand this? So here I've got alpha circles. These are alpha arcs and these are beta arcs. This is an alpha arc and a beta arc. So in here there's some coloring. And if I drew an odd number of sides, then I'm screwed. I need to add another one. But anyway, I want to put the base point z right inside of that big polygon. Single polygon also has all tutorial. Now, and 3 manifolds can always be found, and well, that was great. Unfortunately, they can be a little bit impractical. So like that, you might get a huge numbers of generators. So that's somehow not the end of the story for Heegaard-Floer homology. Another more important point is that I've been there are use a little. An HIS about say talk, but it doesn't has holomorphic. So bordered Floer homology. So bordered Floer homology is Floer homology. Say something about the formal structure of the package. A of F. Now, I'm working on, I should never say the word, but that's nervous. It's not manifold composition. Graded algebra. Oh, sorry. And this is joint work with Dylan. To a surface with a two-handle decomposition and with a handle decomposition and a differential graded algebra, to a three-manifold with boundary F. So as a bordered manifold boundary to the boundary of Y. This is okay. So phi is a diffeomorphism from F to the boundary of Y. And to that, I'd like to associate a right A module. It's a thing that I got a disk and I've got handle pairs. So it's specified by taking a circle, and I got pairs of points on that circle to which I'm supposed to think of as my surface circle as the boundary of a disk, and I'm supposed to think of my point pairs as being the feet of one handles that I attach. And I want my pairs of points on the circle to have the combinatorial property that when I've finished doing this, I have a single boundary component left, rather than two. And that's actually what we call that. That and three maps a bordered boundary, then to that I associate a right module, and to a three-manifold Y2 whose boundary, so I can think of this as the surface associated to a point in matched circle. If I've got a three-manifold and a diffeomorphism from here to minus the boundary, then I associate to that a left module over the surface algebra. And there's the following theorem. Which says that the Heegaard-Floer homology of Y1 union Y2 split along a surface F is the tensor product of the right module associated to Y1 tensored with the Floer homology of the other piece. This is what we call the pairing theorem. So this tensor product is actually a few apologies. This is, in fact, not an honest right module. It's an A infinity module, and tensor is a kind of and tensor product is the as HF hat of this three manifold. Now, avoid page. With bordered boundaries presented by a certain kind of Heegaard diagram. So you're supposed to imagine, this is my Heegaard surface. And my Heegaard surface has bound, you know what I should really say? I should say the point of where this comes from. This comes from the following picture. Suppose I have a Heegaard diagram And I want to compute the holomorphic disks in the G-fold symmetric product. And it's got these alpha circles in it and beta circles in it. But suppose that we can find a separating arc in the Heegaard diagram which crosses only alpha arcs, alpha circles. Then you can imagine trying to pinch the complex structure here and counting holomorphic disks in that limit. And that's actually sort of the motivation behind bordered Floer homology. So we have, in fact, if you cut this picture in two, then you can give a topological interpretation to this piece. And this is this bordered diagram. So great. So all right. So I got my base point z here. And what I'm going to do is I'm going to just define an example of the algebra associated to a surface. And in this case, the surface in question will be the torus. And the way we see the torus is we've got this circle here, and the alpha arcs come out in pairs, two matched pairs like that. So if I try to build up my surface again, I get a genus 1 surface. So this is I'm going to describe for you the algebra associated to a torus. It has generators which correspond to the regions between these red. So the red arcs meet the bound. This I'm supposed to think of. My Heegaard surface is right here. This circle is the boundary of the Heegaard surface. And the red arcs go out to the boundary and they meet it in these red dots. And the arcs that generate my algebra are going to be the arcs that connect the various red dots. So I've got an arc row 1, I have an arc row 2, I have an arc row 3. I, of course, have an arc row 1, 2, and I have an arc row 2, 3, and I have an arc row 1, 2, 3. And there's an obvious multiplication that you get by juxtaposition, with the understanding that if, like for example, row 1 times row 2 is row 1, 2. But row 2 times row 1 is 0. I don't know if that's obvious, but that's the way it is. So I'm going to think of this pair of points as, so you could draw this algebraically, as a kind of quotient of a path algebra. I've got a white dot and a red dot, and I've got a path that goes from red dot, row 1, row 2, row 3. We look at the algebra of paths, except I quotient out by row 2, row 1, row 3, row 2. And I set them to 0. That might be right. OK, so that's going to be the algebra associated to a genus 1 surface. There is 0. It's a DG algebra with 0 differential. OK, the differential comes in, I forgot, higher genus, but I want to avoid that right now. So now that's actually the algebra we're going to associate to a torus. To this particular Heegaard diagram, this Heegaard diagram represents a solid handle body with boundary, the torus. But let me just look at generators. I've got a single beta circle. In this picture, you could imagine changing the picture, and then maybe it's a little bit more interesting. If I change the picture like that, then I've got a single beta circle, but there are two different intersection points of the of that beta circle with the alpha arcs. One of them is called x, and the other one's called y. And in this case, we would define there's a holomorphic disk, just an ordinary disk. If you think of this as a cylindrical end, then I have an ordinary disk that goes from x to y. Except it goes out to the boundary along row 3. And in my algebra, so now I'm defining this CFA hand of y. In this algebra, I'm going to think of that as an M2. So I have the algebra element row 3. It acts on x and it spits out y. So that's how row 3 acts on x to give you y. Let me go back to the earlier example because it has some funny algebraic structure. here I've got a single generator for this Heegaard diagram. I have a single generator X, but I do have a holomorphic disk, you see. I have a holomorphic disk that goes out to the boundary twice. So when he goes out to the boundary once, he picks up a row 3, and when he goes out the second time, he picks up a row 2. So this says that if I act by row 3 and then row 2, then I get X. So this is an M3 in an A infinity module. So just to recall, an A infinity module is a module with an action by a differential graded algebra. It's got, in fact, a bunch of actions, one for each integer. So it's got something that you would call an M1 with no algebra inputs and just a module input and a module output. It's got an M2, which has an algebra input and a module input and spits out a module output. And the next action has 2 algebra inputs and so on. And it's supposed to satisfy a certain compatibility condition. And the compatibility condition says that if you consider a standard tree with a single module input, single module output, and n-1 module algebra inputs, then you look at all the different ways of inserting an edge into that vertex. And you sum over them. And that sum should be 0. So like, for instance, I'll just do a case right here. So if I've got 2 algebra inputs, I've got 4 algebra inputs, like this, then that corresponds to the following kind of relation. There's a relation where I take some clump of these algebra inputs and then follow it by another clump of algebra inputs. And there's also the possibility that I could do some action on the algebra. Now, our algebra, this doesn't make any sense because our algebra is a differential graded algebra. So when I insert an edge this way, the algebra nodes there have to be 2 incoming algebra nodes. So this would be an example. In the case at hand that we're looking at, I have 2 algebra inputs, row 3 and row 2. So I could do this disk, and then I could do it again. This has to cancel against something. It can't cancel against a term where I've got a single algebra input and then 3, because there are no disks that go out to the boundary only once. So that's not an option. Does anyone see a term that could cancel it? The only possible term that could conceivably cancel this is this term. So here I got row 3, row 2, row 3, row 2. Row 2 times row 3 is a valid algebra element. You see, row 3 times row 2 is 0 in our algebra, but row 2 times row 3 is not. So what I'm claiming is that this thing must cancel against a non-zero term like this. But you can see that term geometrically as well. That term is another holomorphic disk. I've got a holomorphic disk that goes out to the boundary here, row 3, comes out, comes back, row 2, 3, comes out, come back, and goes in here. Might be a little bit hard to see it in here, but if you look in the universal cover, you can just see an honest disk. So the punchline is that this is an A infinity module, and it's got kind of all the actions that you can write down, starting with a row 3, writing down as many row 2, 3s as you like until you get really tired, and then you write a row 2. All of these are the non-trivial actions here. Great. So I have defined the type A module at least in one example, but maybe you can imagine how it goes in general. 5 minutes, great. OK. You see, I didn't just define the algebra, because I didn't even define the algebra. Very good. OK. All right. So well, the accounting on the other side looks different. If I flip this picture around and draw it like this, then I'm going to interpret the same disk differently. I'm now defining the type D module. On the type D module, I'm going to have a single generator, X. But this is now not a generator over Z2, but you should think of it as a generator over the entire algebra. So the differential of this X, again, there's this holomorphic disk that goes out to the boundary twice. But rather than interpreting it as an M3, I'm going to just interpret it as saying that dx is equal to rho 2, 3 times x. And that's it. That's the only, so that is to say, if I have a holomorphic disk in this picture, it goes out to the alpha boundary along some chords. And my differential is going to count rigid holomorphic disks from x to y. It's going to say the differential of x is y times the algebra element you get by multiplying together all these chords. So I'm now just looking at this similar kinds of holomorphic disks, but interpreting them completely differently. And that's the type D structure. Now, the tensor product between the type A structure and the type D structure. So let me say algebraically. The type D structure you're supposed to think of as it has a modular element, and the differential spits out an algebra element, time tensor a module element. And the fact that this determines then a chain complex over the chain complex, which is the algebra tensored with our module. And the differential is induced by this map from x to A tensor x. I just multiply on the A side. And d squared equals 0 here is supposed to be interpreted as the following structure relation, which says that the multiplication, if I apply this differential twice, then that's supposed to cancel against this term, where I'm here differentiating on the algebra. This should be 0. So this is the kind of algebraic structure that our type D structure gives. And now I can define what I mean by this tensor product. The tensor product of a type A structure and a type D structure has differential given as follows. There's a term where I just differentiate on the type A side, on the A infinity module side. There's a term where I differentiate on the module side that spits out an algebra element, which comes in and M2 acts on the algebra on the A infinity module side. There's a next term where I do differential twice, get two algebra elements, they act at the same time on the A side, and so forth. I don't know if this is clear. So in general, I've got a tower where I'm applying the differential on the D side a bunch of times. That gives me a sequence of algebra elements. They act at the same time on the A infinity module side. So this is what the typical term looks like. I should, what? Stop. OK. Well, OK, so this satisfies d squared equals 0. It has a homology, and that's the right-hand side of this equation. And then after another 15 minutes, we compute the spectral sequence that I stated at the beginning of my talk. So, OK, I still never made it, but I gave it a shot. Yes?
Curtis, can you see the easy relationship between CFP and Floer?
I'm not the person who's supposed to answer that question. Yeah, this by Denis. Denis wrote a paper in which he identified the type. Our modules with a sort of partially wrapped Fukaya category. And what else did you ask? Right, OK. Yeah. Denis has a paper about that. OK, so maybe I should stop. Sorry.